Group 14 elements. See, the group 14 elements mainly contain carbon, then silicon, then germanium, then next is tin, then the last one is lead, that is plumber. Simply, they are called carbon family. So the carbon family contain carbon, silicon, germanium, tin and lead. Here, this is the they are called group 14 element or member of the group 14 element. So here the carbon is the 17th. It is the 17th most abundant element by mass in the earth crust. See, it is widely distributed in nature. They are available in free state as well as in the combined state. So the elemental state is available as coal, graphite and diamond. However, in combined state it is present as a metal carbonate, hydrogen carbonate, the hydrocarbon, then carbon dioxide gas, like that. That is in air. See, here it is combination. That is that this is mostly most versatile element, and it is combination with other elements such as dihydrogen, oxygen, dioxygen, chlorine, like that. So sulfur, they provide the astonishing array of the materials ranging from the living tissues to drugs and plastics. Okay, so the here usually in organic chemistry it is devoted to carbon containing compounds. This is a essential constituent of all living organisms. So here the naturally occurring the carbon contains two stable isotopes, that is carbon 12 and that carbon 13. Carbon 12. See, the third isotope also possible, that is carbon 14. Here these two are more stable, so the carbon 14 also available. That is here the radioactive isotope, that is the half-life. This is the half-life radioactive isotope. The time is 770 years only. See, this is used for a radiocarbon dating. That is radiocarbon dating. We can measure the life. So that is some elements like a tree. So that using the carbon dating, so we can calculate the years. Then next is a silicon. That is silicon is the second most abundant element on the earth crust and present in nature in the form of the silica and the silicate. Then next is a germanium. Germanium is only exists only in traces. Tin occurs mainly in the crystalline, that is tin oxide and lead galena, that is lead galena, like this. Here the germanium and the silicons are used to make transistor and the semiconductor devices. Okay. Then we will see the electronic configuration. So electronic configuration, that is the general outer electronic configuration, or simply we can write NS2 NP2, NS2 and the NP2, and the inner core of the electronic configuration of the elements group also differs. Just this is outer electronic configuration. So simply they end with NS2 NP2. Then the covalent radius. The covalent radius is usually increases from carbon to silicon. Carbon to silicon, the covalent radius are increases. Then thereafter from silicon to lead, that small increase in radius is observed. Okay. Then why this reason is the presence of the completely filled d and f orbitals in the heavier member. Okay. Next is a ionization enthalpy. Or we can write it ionization enthalpy, that is delta H ion. Here the group 14 elements, the first ionization enthalpy is higher than the group 13 element. That is before section we studied the group 13 element. The influence of the inner core electron is visible here also. That is why ionization enthalpy is higher. So the ionization enthalpy generally decreases down the group. The small decrease in the ionization enthalpy, silicon to germanium, then germanium to tin, and slight increases in ionization enthalpy from tin to lead. So this is the consequence of the poor sealing effect of the intervening d and f orbitals and increases in the size of the atom. Okay, so this is the ionization enthalpy. Then electronegativity. Electronegativity is small size. Due to small size, the elements of this groups are slightly more electronegative than the group 13 elements. So the electronegativity values, elements from silicon to lead are almost in the same. Next is the physical properties. So the physical properties, all the group 14 elements are solids. The carbon and silicons are non-metals. Germanium is a metalloids. Tin and leads are soft metals. They have a low melting points. The melting point, boiling points of group 14 elements are much higher than those of the group 13 elements. Next is the chemical properties. The chemical properties, we will see here the oxidation states and the trends in the chemical reactivity. First we will see the oxidation state. Here the group 14 elements have 4 electrons in the outermost cell. How it is? That is ns2 np2. So here totally 4 electrons in the outer cell. So the common oxidation state exhibited +4 and +2 is possible. This is the common for all elements. Here the carbon also exhibits negative, that is carbon also exists the negative oxidation state. Some of the first 4 ionization enthalpy is very high. Then the compounds in +4 oxidation states are generally covalent in nature. Here then the compounds having, that is in heavier members, the heavier members like the lead, tin, like this, the tendency should show that the +2 oxidation state, that is the order is germanium is less than, tin is less than lead. Okay, that is oxidation states are increases like this. So why this reason means inability of the ns2 electrons of the valence shell to participate in the bonding. Here the relative stabilities of these two oxidation states are vary down the group. Okay, +4 and the +2. The carbon and silicon mostly shows +4. Carbon and silicon shows +4. Then the germanium forms the stable oxidation, that is stable compounds of +4, and only few compounds in +2. Okay, germanium is mostly stable is +4. Some few elements, so it shows +2 also. Okay, then the tin forms both oxidation state in the +2 is a reducing agent, and the lead compound shows a +2 is a stable, and its +4 state also strong oxidizing agent. So it is in a tetravalent state, the number of electrons around the central atom in the molecule. Example, the carbon tetrachloride. Okay, that is the central metal atom molecule is here is 8. Okay, the here the being the electron precise molecule, they are normally not expected to act as a electron acceptor or electron donor species. Okay, that's mean electron precise means completely fulfilled. They don't need electron, or they do not donate electrons. Okay, then reactivity towards oxygen. Reactivity towards oxygen. See, all members when heated to oxygen forms oxide. There are mainly two types of oxide, that is monoxide and the dioxide. Simply we can write it, that is monoxide, that is dioxide, MO2. Here the silicon, that is SiO. Silicon only exists in high temperature, that is silicon oxide. The oxide in the higher oxidation state of elements are generally more acidic than the lower oxidation state elements. So the dioxide like carbon dioxide, sulfur dioxide, silicon dioxide and germanium dioxide, like this, so are acidic, and these are acidic, and that SnO2, that is tin oxide and lead oxide, so they are amphoteric natures. Amphoteric nature. Then the carbon monoxide as neutral. Then germanium oxide. Germanium oxide is distinctly acidic, whereas tin oxide and lead oxide are amphoteric. Okay. Then reactivity towards water. So generally carbon, silicon, germanium does not affected by water, but tin decomposes steam, form dioxide and the hydrogen gas. For example, tin react with water. What happens means that this means on heating it gives tin oxide, then there is dioxide and dihydrogenous form. So lead is unaffected by water, probably because of the protective oxide film formation. Next is the reactivity towards halogens. Reactivity towards halogens. Usually elements can form halides of formula like MX2. Here X indicate fluorine, chlorine, bromine, iodine. Except the carbon, all other members react directly with halogen under suitable condition to make halides. See, most of forming like that's MX4. The MX4s are covalent in nature. Then the central metal atoms, these halides undergoes sp3 hybridization, sp3 hybridization, and the molecule is a generally tetrahedral in geometrical nature. So exceptions like strontium tetrafluoride, lead tetrafluoride, which are ionic in nature. Then lead iodide, tetraiodide does not exist because of the lead iodine bond initially formed during the reaction does not release the enough energy to unpair 6s2 electrons and excite one of them to higher orbital to have 4 unpaired electrons around lead atoms. That is, the heavier members like germanium and lead are able to make halides of formula like mx2. The stability of the dihalides increases down the group considering the thermal and the chemical stability. Okay, here the germanium tetrahalides are more stable than the germanium dihalide. Similar, whereas the lead dihalide is more than lead tetrahalide. So except that carbon tetrachlorides and other tetrachlorides are easily hydrolyzed by water because the central atom can accommodate the lone pair of electrons from the oxygen atom to oxygen atom of water molecule in the d orbital. That hydrolysis can be understood by taking the example of the silicon tetrachloride. It undergoes a hydrolysis by initially accepting the lone pair of electron from water and molecule that d orbital. So that is the d orbital of silicon. So finally leading to the formation of the silicon like this. So the silicic acid, they are called silicic acid. We can see the reaction, that silicon tetrachloride. So they have like this. So this is silicon tetrachloride. When react with water, so what happens mean, this lone pair of electron to tag this silicon atom, then removal of the HCl, one hydrogen from this, so removal of the HCl, that remaining OH group going to join here. That's mean just simply like this, removal of HCl. So forms OH, Cl, Cl and Cl. Then again addition of 3 moles of water and the removal of similarly 3 moles of the HCl. So 3 Cls are there, that's why 3 moles of water is added, then removal of 3 moles of that chloride ion. So you will get silicic acid. Okay. Next class we discuss important trends and anomalous behavior of the carbon.